Everyone. My name is Kayla Youngblood, and I will be presenting on some research that I did at Caltech over this past summer with Sarah Reisman. I'll be discussing synthetic methods for non-symmetric. So I'll begin with a little background, get into reaction development, and then move on to future work. So with background, let's get into some biological significance, established synthetic methods, and the project. So you might be wondering, what exactly is a phenazine? Phenazines are a class of natural products that have a wide variety of structures. So this core highlighted here in maroon is what we classify as the phenazine structure. So we can find these in several different places. One area is the rhizosphere. So the rhizosphere is the root system of plants, and there's bacteria that live down in there that produce these natural products. And these are really of interest to chemists and biologists alike for their antibiotic properties. So these are redox-active compounds, and they go through a unique antibiotic pathway. And so we think that there's a possibility these might be an effective antibiotic in cases where bacteria have developed antibiotic resistance. One of the issues, though, for biologists wanting to study the activity of these compounds is you have to isolate it from the bacteria in these root plants. And it's difficult to gather large quantities of material in order to study these compounds. So that's where synthetic chemists come in, and we want to develop a way to make these compounds. So some of these have already been synthesized. Mixin was synthesized by Victorson et al., who what we call a cross-coupling. So we take two identical pieces, link them together, and go through this symmetrical intermediate that we can then mess around with and manipulate to get to the non-symmetrical product mix-in. But as you saw on the previous slide, there's a wide variety of compounds that are really complex, and a lot of them are not symmetrical in the end, like PCA here, for example. So we wondered if there was a way to develop a general synthesis that could be adaptable to any phenazine. We just took the work from Victorson et al. We want to manipulate it to adapt it to linking two non-identical pieces together. So in the first scheme, you can picture linking two Legos together that are identical. The second piece would be linking two non-identical Legos together that we can build on. And that's where the project goal came from, was to develop a versatile route to non-symmetrical phenazines. So with that, I'll get into some of the reaction development and how we went about this project. So to begin, we took this synthesis from Victorson et al., and we keyed in on this synthesis highlighted in blue. That's the cross-coupling step. And that's what we really wanted to manipulate and play with. So we started out with this pretty simple non-symmetric coupling. And this slide highlights the key struggle of this project is there's three possible products. So compound 1 could link up with itself and give us product A. The number 1 and 2 could link up together, give us product B, which is desired. And then compound 2 can link up with itself and give us compound C. And we wanted to figure out how to prioritize getting one of these products over the rest. And so under these conditions, we never saw synthesis or production of compound B. In entry 2, we see a little bit of compound A, but mainly we saw production of compound C. And so we wondered if maybe it just wasn't favorable to have this type of functional group. So we switched it around a little bit. And instead of the O-methoxy group, we put on this ester group instead. And so pretty quickly, right off the bat, we saw synthesis of B and 10% yield, which is our desired product. Yet we still saw synthesis of C, and overall, these yields weren't great. We kept messing around with different ratios of material, and we weren't able to reach that 10% yield ever again, as evidenced in entries 2 through 4. So then I wondered if it was that these were too air sensitive, so I tried 2 different types of air-free techniques and got no yield of any product at all, and this was also on a larger scale. When I used a new bottle of catalyst, I was able to produce compound B in 10% yield, I was also able to produce compound A in 23% yield, which we had never been able to synthesize before. And so this taught us that catalyst health was really important to the success of these compounds. And so here's another example. So previously, only one of our puzzle pieces had a functional group on it, and here we had two. And this is a really exciting project we are working on, because if this could be successful, this would teach us a lot about the mechanism of the reaction and the applicability of the reaction. And so these compounds were never able to be isolated. We did see masses on an LCMS that corresponded with product B, but we were never able to isolate those, unfortunately. So that's just a brief overview of all the work that went into the project. So now I want to discuss the future work. Overall, this project demonstrated that this is a promising route to phenazines. So we were able to synthesize the center compound in 10% yield. And as this project was just getting off the ground floor, it's envisioned that this yield could be improved, and these could afford us access to several natural products, some of which have never been synthesized before, including Endophenazine A. And this would link to our collaboration with the Diane Newman group at Caltech, who was studying the biological activity of these compounds. And with that, I just want to thank the team of people I worked with, Dr. Sarah Reisman, Lexi Beard, and Dr. Connor Farley, for all of their support in this process.